Today we're going to be talking about power series. This is the start of chapter 11. Possibly one of the most useful tools in all of calculus, to be honest. It's really, it's a powerful idea. So what we've had so far is we've looked at series, which are things that look like this. They've got a summation with, how about we start at 0 and go to infinity. So an infinite series with terms a sub n. If I want to convert such a thing to a power series, all I'm doing is adding in x's a variable, right, to a power. So the power series looks like this. It's got the same decorations on the outside. In fact, you may call the thing, oh, I'm sorry, I used I as the variable, and so this should have been a sub I. And this will be a sub I. But the other piece that'll be in here when we've got a power series is x raised to the I power. Cool. That's not a huge difference, but now it turns the thing from, this one is just a number, right? What is this one? Well, it's a thing that has x's in it, so that thing's a function, right? It takes x and produces, a value for each x. I think that's probably worth really emphasizing. The infinite series is a number, or well, possibly not a number if it's a divergent series. But this one is a function. And, or, of course, possibly not a function too. If this thing diverges for all values of x, that would be bad. But you should notice that when, for instance, x is 0, this whole thing is just going to give us zeros. Or will it? No, because even when x is 0, the first term is 0 to the 0 power, which we usually, by definition, consider to be 1. So you'll get an AI out of that. Anyway, right, number or possibly infinity, a function, possibly with some regions where it's not defined. What I'm about to tell you may not seem related, but you have to trust me on this, it is. I want to tell you this little anecdote about when I was working for the Naval Research Laboratories. They do a lot of astronomy there, and a particular group that I worked with did astronomical stuff. And the guy who led that division was an astronomer. So I was looking through some computer code that was trying to, one element of it was trying to figure out, so you have sort of a sensor. I'm going to draw it as if it were a human eyeball, but it really would be some sort of, telescope in orbit. Like, think about the Hubble telescope, for instance. And it's looking out at a star field off in the distance. And in particular, if it's looking at something where you know the distance to the thing you're after, that you're observing, so this distance to an object out here is known. Let's call it d. What I needed to calculate, or what needed to be calculated, and there was a bug in the program, so I was looking for where's the error, right? What needed to be calculated was the size of this field of view, with d units out. And what we knew was the angular resolution of the sensor. So that is, you knew that there was a triangle, basically, that went out to this area you were looking at, had a right angle in there, and some angle theta in here. And so you guys are good with this. If d could be reasonably thought of as either the hypotenuse or the adjacent side, because it's a really long, skinny triangle, right? So I think we were thinking of it as the hypotenuse. So it was actually d on that leg of the triangle. And figuring out this unknown quantity here, let's call it, well, I guess I'll call it x, right? X would be equal to, well, x divided by d would be the sine of theta, so x is equal to d times the sine of theta. Right? So that's roughly what we were thinking. I mean, basic trigonometry, right? That's not an issue. But what I noticed in the code was this. They didn't have d times the sine of theta. They just had d times theta. And I was like, found it. I got the bug, you know. And so I went to Harry, the boss man, and said, here's the issue, Harry. They were supposed to use the sine of the angle at this spot, and in fact, they just used the angle. And he goes, well, what unit are the angles in? And I said, well, they've been converted to radians. And he said, then it's fine. And I was like, what? No, it's supposed to be the sine. It's like astronomers use this approximation all the time, that the angle and the sine of the angle are the same number. So that's why you use radians. And then I felt like an idiot because I was the mathematician on our crew, and sure enough, that's exactly what the reason for radians is. Yeah. So what's going on in that in fact it's perfectly fine to substitute theta for the sine of theta. Let me draw a really giant graph of the function y equals sine of x. Or maybe we should call the x-axis the theta axis in this instance. So we'll have y equals the sine of theta. It looks more or less like that if you're zoomed way in on it, right? And the line, this is y equals sine of x. The line of the graph, sorry, I keep saying x, but I just said it was theta. The graph of y equals theta is this line, whose slope is 1. Right? And the problem is that, well, the why this whole thing works is that for small enough values of theta, these are indistinguishable. Right? That you can see the line is right on top of the curve down in here, and it just barely begins to separate it from out here. So this is called the small theta approximation. That is, sine of theta can be approximated with merely theta when theta is small. Now, what do we mean by small? Well, really you could use sine theta as theta for any angle, but your approximation would stink. But when theta is small, you can say this approximation is good. In fact, you can put numbers on how far off it is. So how small are these angles we were talking about? Well, the particular satellite system we were looking at was in geosynchronous orbit, which is maybe, I don't know, 30,000 miles out, something like that. So the distance was 30,000 miles from the sensor to the thing it might be observing, and its angular resolution was in the fractional part of an arcsecond. The resolution was something like 1/10 of an arcsecond. So you have to think about how big of a number that is. When I say an arcsecond, that's in the old style degrees units that come to us via ancient Babylon. So that's a pretty antiquated thing. Let's turn that arcsecond thing into radians, so we'll get an idea of how big this number is. So 0.1 arcseconds is, you divide that by 60 to get it into minutes. Because 60 seconds in a minute, right? And then you divide that again by 60 to get it into arc degrees. So it's equal to 0.1 over 60 squared, or 3,600 degrees. Not a very big number. And then to convert something that's in degrees into radians, let me kill this since we need the space. 0.1 divided by 3,600 is the magnitude of that angle in degrees. To get it into radians, we times by pi over 180. I think you've probably done that fairly recently. So, shoot, I guess I should have had a calculator handy. So here's my calculator as if by magic, and the answer came out to be about 5 times 10 to the minus 7. If you want to know something about the decimals, 4.85 times 10 to the minus 7 radians. Or if you write it out as a decimal, let's see, put 1, 2, 3, 4, 5, 6 of those, then the 485. Right. So I guess what I'd like to do is take this number that's in my calculator already and calculate the sign of it and see how different it is from that number itself. So that is, I'm going to take the sign of the number we're looking at, which is sign of the previous answer, minus the actual answer. And, oh, my calculator says it's 0. The reason is, can you see that? It's 0 because the difference between those numbers, there is an actual difference between them, but it's well beyond the ability of the calculator to discern. So it just thinks it's 0. As far as the number of significant figures that the calculator can hold is concerned, the two values are exactly the same. Which is what my boss was trying to put across to me back in the day. So why am I talking about this? Because what we're dealing with there in that particular example is what's called a linear approximation. Y equals x is a linear function that very well approximates the sine of x. Can I continue that word over a line? Approximates sine of x. Provided that you use small values. If instead of the sine of x, I wanted to have an approximator for the cosine of x, think about what the graph of cosine looks like. It's got a hump there in the middle, and then it goes like that. Well, for small values of x, just a horizontal line will do the trick. Now, that looks like it deviates from the graph a lot, but again, imagine yourself zoomed in, so you're only seeing, that graph in a tiny little region where the angle is quite small, and you really wouldn't be able to see the difference between those. So y equals 1 is a good approximator for cosine of x. But with cosine of x, you probably see the kind of next stage up that you might want to do. If I wanted to go to a better approximator for this, kind of what I would like to do is create a polynomial. It's going to be just a parabolic polynomial, or a quadratic, right? Make a polynomial that has the same slope as this. Well, I found the clear marker. Okay, how to get rid of that one? It has the same slope as this guy here, but it should also be curved in the downward direction like the cosine graph is. Now, I don't know how that's going to look overall. I mean, if it's a parabola, it's going to keep heading downward, whereas the cosine graph turns around and heads back up, on both sides. But you could get a quadratic that very closely matched the value of cosine of x. And let's play with that a little bit. How would we get such a thing? Well, imagine you have a quadratic polynomial, just generically. You don't know what these coefficients are, but it looks like ax squared plus bx plus c. So in terms of those coefficients, a, b, and c, you can tell me what its derivatives are, what y prime would be. Y prime is 2ax plus b. And also, take a second derivative. You can do that too. You get just twice a, don't you? Right. So for a quadratic polynomial, these are its derivatives. And if you evaluated it at 0, if in fact you can evaluate all of these things at 0, evaluated x equals 0, you're going to get C. Evaluate this one at x equals 0, you'll get B. And this one evaluated at x equals 0, well, it doesn't matter where you evaluate that one. At any point, its value is twice A. So the coefficients actually appear as the constant is the value of the thing at 0. The first derivative ends up being the value of, the first derivative evaluated at 0 ends up giving you the linear term, or the multiplier on x. And except for this factor of 2, you get A out of the second derivative. So let's think about our cosine graph. Its value at x equals 0, we're here right at the origin, or right above the origin, the value is x equals 1. Excuse me, I just said x. The value would be y equals 1. Its slope, that's the value of the derivative, its slope is 0. And the second derivative tells you, essentially tells you how curved it is. Is it concave down or concave up? So I'm just going to say curvature in quotes because that's not quite the right number for curvature. It's off by a scale factor, but it's close enough. The curvature of it is its second derivative evaluated at 0. Shoot. I could see that the value was 1 and that the tangent line was horizontal, so the value and the slope were easy. But I actually have to do a calculation to figure out the curvature part, the second derivative. Y is cos x, so y prime would be negative sine x. So y double prime, that would be negative of cosine x. Okay, so its curvature is y double prime evaluated at 0, which is negative 1. So what we're going to do is get our parabola to match our actual function with regard to these three things that are just, these are geometric items, right? These are things about the function that don't sort of depend on the details of it. You know, what's your value? What angle are you moving at? And how are you bent? Those are geometric descriptors of the thing. So if we make the parabola have geometric descriptors that match the geometric descriptors of the cosine curve, they ought to look a lot alike. So I'm going to go do that on Desmos, but let's just see, what would the A, B, and C be? We can read them off of here. C would be 1, B would be 0, and twice A would be minus 1, so that makes A, I guess it's negative a half. As promised, here we are looking at a Desmos graph. I've already plotted y equals cos x here. Let's zoom in a little bit so that we can see the region we're interested in. Now, you can see that this is not really going to be a parabola, I think. You know, the fact that it is curved downward at first makes you think, yeah, all right, but then it does curve the other way after not too long and ends up heading back upward, so not really a parabola. I did figure out the right coefficients to use a second ago, but why not just try leaving them as indeterminates? So y equals a times x to the second plus b times x plus c. And when you do that kind of thing using variables or constant variables as in an expression, it gives you this option of adding sliders. I'd like sliders for all of those. Now, what did we know before? C is 1. Oh, perfect. C is already 1. Now I moved it and it's no longer 1. Let me just type that it's 1. C is 1. That's where you pass through the y-axis. That's your y-intercept. I believe we had decided that b had to be 0. And when we set b to 0, you end up getting something where the vertex of this parabola is right there on the y-axis. And then y needed to be negative. Now, how much should we make? Well, that looks like it's about the right spot. No, that's a little short. Okay, so the limits on y there are a little, on a were a little bit too coarse. That is, they were over too wide of a range. So I'm going to go between 0 and -1 here. And now we should be able to adjust it with a more fine-grained way. Accidentally hit the middle button. That looks really pretty good right in there. Well, what did we say before the value was? It was exactly -0.5. And doesn't that look great there? If we zoom in so that we're just seeing those two things near 0, it doesn't take much of a zoom in before you really can't see the red one at all. I'm honestly not that far zoomed in. I can see just the faintest hint of red around the tops of the line here, but the width of this interval is about, well, it's about 1, going from about -0.05 to +0.5. 1 radian is a large amount of angle, and it's like 57 degrees, I think. 50. Anyway, it's big, and the kind of angles we were dealing with in astronomy would be way down in here. It's already at this scale I'm at now, with the width of the view is about about 0.3. Yeah, it's already clear that those two things are indistinguishable. All right, so why have I been looking at these things? What I've been showing you actually so far are just a linear and then a quadratic approximation to a polynomial. The general idea is that if you have, I think I just said that wrong. So let me try again. What I've shown you was the linear and quadratic approximations to functions, the sine of x in one case and the cosine of x in the other case. The general idea is that if you're given a power series, so some infinite sum, it starts at 0, goes to infinity, of a sub n x to the n. Darn it, I just made n's for the index variables, so let's make these be n's instead. All right, I'm going to try that over again, because I really want i's to be the index variables, because n is going to mean something else. So I goes from 0 to infinity of a sub I x to the I. What the partial sums of this thing are polynomials. That is, they look like, a function, let's call it p of x because I think it's a polynomial. It is a finite sum that goes from I equals 0 to some number n, right? And it has those same terms in it, ai x to the I. So that upper limit, n, that's the degree of the polynomial. Now, it turns out that most, if not all, of our, in a certain sense, all functions we might be interested in are actually expressible as power series. And so these partial sums become closer and closer approximation to the power series. And since and in fact, they often, the partial sums maybe hold most of the answer, and the tail of the series is something that's inconsequential in practice, especially when x is small. Its powers end up being, very small. And so the later terms of in a power series can often be seen to go to 0. All right, so that's the main deal here, to think about coming up with a sequence of polynomial approximations that get better and better and better at approximating a real function. I think I'll end this by just giving you one example of such a sequence of things. Let me kill off all the work we just did and replace this function cosine of x with e to the x. Oh wow, I'm pretty zoomed in, aren't I? Not that far zoomed in, but okay, so now that looks more like e to the x. Okay, now I'm going to plot for you a succession of better and better approximators to this. The first one I'm going to do is only going to have the right value, and so it's just y equals 1. Okay, it's terrible, right? But if you have a number that's very, very, very close to 0, the value of e to that number is very, very close to 1. A second approximator would be something that matched not only the value, but what's the slope of our function. Now, what is the slope of e to the x when x is 0? Well, its slope is 1 because its derivative is itself, and you stick 0 into e to the x, you get 1 again. So to have a value of 1, that means your y-intercept is 1, and to have a slope of 1 means the m is 1. Well, here's the curve. It's y equals x plus 1. Okay, now the green graph, maybe I'll turn off the blue one. The blue one sucks, but the green one isn't bad. For an appreciable interval in here, it looks like maybe between negative 0.1 and positive 0.1, you can't even see the red graph. But, if we're a little bit wider out, you can. All right. Well, all right, so what I would like now is to get an even better approximation. It turns out it's got the things we had before. Let me write it this way. Y is 1 plus x plus, now I want something that sort of captures the second derivative information. And it's not x squared. Let's just put in what x squared would look like. X squared isn't bad, but it's not quite the right number. What you really want is x squared over 2. Why do I want that? Well, what's the second derivative of e to the x? No problem. E to the x's second derivative is always, well, any derivative of it is always e to the x. And you plug in x equals 0, you're going to get 1. So all of the derivatives of e to the x are going to be 1. That's a useful thing to remember. What's the second derivative of the graph I have right here? The constant term is going to be gone. The linear term is going to be gone. Only the quadratic term will survive. And the value of this guy's derivative is 1. X squared over 2. When you take two derivatives, you get 2x over 2. You get 2 over 2, you get 1. Okay. I was doing that mental math there, but check me on that. So why is x squared over 2 is the right thing so that we match the value, the derivative, and the second derivative of e to the x. So let's turn off the other graphs. Notice how good that is? The purple graph or bluish graph is really quite close to the other thing. How could we make it a little better? Well, what really we're going to be doing is adding more and more of the terms of the series. But let's try to match the third derivative. Right? What would the third derivative of e to the x be? 1, right? How could we change this polynomial so that its third derivative was 1? Well, notice the third derivative would kill off all the terms that have degree less than 3. So only the degree 3 terms of the polynomial would survive. And wow, that's a tough one. We should quickly take a look at that. if I have a third degree term that looks like ax cubed, then it's, if y is that, then y prime is 3ax squared, and y double prime is 6ax, and so y triple prime is 6a. So the derivative is 6 times the coefficient. If I want the coefficient to be, I want the derivative to be 1, then the coefficient is going to need to be 1/6. So let's throw that one in here, plus x to the 3 divided by 6. Wow, it's almost good all the way across the graph, the part of the graph that I can see. And perhaps you're noticing the pattern that's developing in this. What is going on with the numbers and what I'm, it'd be smart for me to zoom in this a little bit, zoom the formula a little bit. We're going to get higher and higher powers. The powers are just going from the 0th, 1st, 2nd, 3rd, and so on. What about the dividing by 2 and the dividing by 6? And I guess here we could have written that as dividing by 1. Well, I don't know if you'll recognize the pattern or not, but maybe some people will. What's going on in the denominators there are the factorial numbers. So this is, the next term would be x to the 4 divided by 4 times 3 times 2 times 1, which is 24. Whoops. X to the 4, got to get out of the fraction, out of the exponent, then divide by 24. Yay. And see, now that, over the range we're looking at, like from -1 to +1, it's indistinguishable from the graph. But, you could always keep going. You know what the next factorial is? It would be x to the 5th divided by 5 times 24 is 120. Really, really quite good again. It seems to grow better and better and better as we take the approximation farther and farther out. So thus far I've got a degree 5 polynomial that's a great approximation for e to the x. And in fact, what we're thinking about here is an infinite process that gets closer and closer and closer to the actual value of e to the x. So we're ready to say what the power series for e to the x is. E to the x is actually defined to be equal to the infinite sum, where I starts at 0 and goes to infinity, of x to the I power divided by I factorial. Now the only piece of that sum that might be freaking you out a little bit, I think, is when I is 0. Because when I is 0, we've got 0 factorial in the bottom, and then x to the 0 in the top. Well, let me just make some notes here. 0 factorial is defined to be 1. That's just, get used to it. That's what we do with 0 factorial, it's 1. And x to the 0, we know is 1. So the constant term in this infinite series, this infinite power series, is actually 1, just like it was when we figured out a good polynomial approximation. And did you notice how all the polynomial approximations were sort of contained in the next one up? That's sort of a useful feature of these things. It happens because when you take the derivatives of things whose degree is less than k, if you take the kth derivative, they get killed off. So those terms don't even appear in thinking about the shape you want for matching the kth derivative. I'd like to take the same approach we just did for e to the x and think about sine of x in a very similar way. It's going to be necessary. Well, the derivatives of e to the x were a little bit easier to deal with, but it's not a huge difference. So let's first figure out what the various derivatives of sine of x are at 0. That is, we're thinking about f of x is equal to sine of x and I want to know what is f's kth derivative, which is often denoted like that, k in parentheses, evaluated at 0. And in fact, I guess I'll make a little table of that. K equals 0. Well, that means don't take any derivatives, so sine of x evaluated at 0 is 0. And when k is 1, the derivative of sine of x is cosine of x, so cosine of 0 is 1. When k is 2, I do think we should probably remember this little like clock drawing I showed you once before about how to remember the derivatives of the trig functions. I'm taking successive derivatives of sine of x, and the thing that's cool is that once you go around a cycle of 4, they just repeat themselves again. By the time you take 4 derivatives of sine of x, you're back where you started. All right, so that's going to help us because the 0 and the second derivatives, those are both sine of x or minus sine of x, they're zeros. And the odd number derivatives, actually, it's all the odd ones that are going to survive. They are either cos x, where you get 1, or they're minus cos x, and that's what happens on the third derivative. You get minus 1. And then they repeat, right? The fourth derivative is 0 again. That's when you're back at sine, and sine evaluated at 0. Right? So I could take this as far as I want, but the pattern is really simple. It skips every even number. It's 0 at every even number, and it's either plus 1 or minus 1 on the odd numbers. In fact, they alternate. So there's the first few of them. And I'm going to show you a sequence of progressively better polynomial approximators for sine of x. The first one is, well, if we did just the 0 derivative, no derivatives, and the linear polynomial we'd get, or the constant polynomial we'd get, would just be 0. I think I'm going to skip over that one. But the one we started with was when we have matches both in the value and the slope. So the first derivative, the first derivative polynomial, the polynomial that matches in both value and slope is y equals x. I think I'll just keep changing this one. The next thing to match the second derivative, we don't need to because the second derivative is 0. So we're going to jump to the cubic terms that have an influence on the third derivative. And we want the third derivative to be minus 1 on this function we're making. And that means we'll be subtracting, and it's not x cubed. I wish it was. That doesn't look so bad, but it's not quite the right number. And this happens because of the way derivatives work. When you take the derivatives of x cubed, you get 3x squared, then 6x, and then just a 6. So you need to divide by 6. This is the same thing that happened for us in the e to the x expansion. Okay, so now I've got something that matches the value, it matches the first derivative, it actually matches the second derivative for free, and it matches the third derivative. And you know, over this range, it looks an awful lot like sine of x. But let's keep going and make it even better. The fourth derivative is 0, so we won't need a degree 4 term in this. What we will need is a positive thing with an x to the 5th in it. I'll have x to the 5th, but it's not just going to be x to the 5th because of that same voodoo about how you take derivatives. What we're going to have there is the bottom is 5 factorial. It's 5 times 4 times 3 times 2 times 1. If you started with x to the 5th and watched what happens as you take successive derivatives of it, you'll end up with 120 as the final thing. So we divide by 120 to make this work out. And wow, look at my red graph. It's just almost perfect now. I can take it one more notch if you want. The next one would have a negative, let's see, it'd be the 7th derivative. It will be -1, and so we'll have x to the 7 divided by 7 factorial. I wonder if Desmos understands the factorial sign. Apparently it does. So, wow, they look indistinguishable at this point. If I back away a little bit, you'll see that the red polynomial is actually different from the thing I started with. But over, looks like from minus pi to pi, they're pretty much indistinguishable, which is cool. You can continue to make it better and better and better. I might as well do it now because it's so easy. See how the powers look? They're always just x to an odd number, and then we're dividing by that odd number factorial. Oh wow! Now look at that. We've got a 1, 2, 3, 4 humped camel here. The number of direction changes is what people normally keep track of. If you throw in one more, it'd be minus x to the 11 divided by 11 factorial. Well, that's still just 4 humps, but you know they get more and more of they match along the graph y equals sine of x better and better as you take the powers to higher and higher levels. I want x to the 13 divided by 13, bang. What? Oh, I'm sorry. X to the 13 divided by 13 factorial. Yeah. And, well, I think probably I'm beating a dead horse now. You see what the pattern is, I hope. So let's see if we can write out what the infinite series would be that has, those are sort of its first several terms. The power on x is x to the 2i plus 1. And that's with I starting at 0 and going to infinity. And then we will be dividing by the factorial of that same odd number that I've just put in the exponent. Now this isn't quite right yet because I mean it's got most of the, well, sorry, it's missing the factorial sign, but it's still not quite right because it's missing the idea that the derivatives were either zeros or ones or minus ones. And in fact, well, let's see if we can match it. When I was 0, our derivatives, let's think about what the values of I are that give us these odd numbers. When I was 0, you get 1. Right? When I is 2, you're getting minus 1. What am I saying? When I is 1, you're getting 3, right, as the 2i plus 1, and that's when the derivative is minus 1. When I is 2, that's when you get k is 5, 2 times 2 plus 1, and the derivative is 1. And I is 3, 3 times 2 plus 1 is 7, and the derivative is supposed to be minus 1. So how do we go straight from the i's to the derivative values? When we're at 1, we get minus 1. At 2, we get 1. At 3, we get minus 1. After a bit, you might notice that the deal is the odd-numbered i's give you minus 1s, and the even-numbered i's get you plus 1s. And we've seen the trick that does that. Take negative 1 to the I power. Now, this is an example of a thing called a Maclaurin series. And we usually separate the parts of the Maclaurin series into 2 pieces. One is what's right in there, which is the derivative, the ith derivative, I guess it's the ith derivative of the function evaluated at 0. That's concerning to me because it's actually the 2i plus first derivative. That's why, because of this deal where all the other we're skipping over the even derivatives. But anyway, we can think of this as the ith derivative. And then the other bit is I factorial. Now I get it that it's 2i plus 1, but that's just a foible of this particular way of writing it. And then finally we've got the power part, that is x to some power. Yeah, again, it's 2i plus 1, not I, but those are the pieces in general. So let me write for you what the beast I've been talking about is. It's called a Maclaurin series. And this works for any function f of x. So it's an infinite sum, and it's got the ith derivative of the function evaluated at 0, and it's got 1 over I factorial, because of the way derivatives work. We're basically scaling the derivative by I factorial, or dividing it by I factorial to make it, to make it match the actual pattern, and then it'll have x to the I power. That's called a Maclaurin series. Sometimes people write these two together. It'll be f's ith derivative at 0 divided by I factorial. I kind of like keeping those issues separate, but it doesn't matter. Now, our book doesn't mention Maclaurin series, and there's good reason for that. Maclaurin talked about his series here after another mathematician named Taylor had already defined this in a more general way. So Maclaurin is actually a special case of Taylor's series, and Taylor came first, so he really oughtn't have his name attached to anything. But I do think the book's attitude on this is a little bit off, because, well, the rest of the world does talk about Maclaurin series, so they exist. You'll hear people talking about them, and it's not really appropriate to just drop the idea. So Maclaurin series, those are Taylor series that are what are called centered at 0. That's what a Maclaurin series is, a Taylor series centered at 0. So what Taylor did, again, before Maclaurin talked about his series, is think about this not just happening at 0, but happening anywhere down the line. You could take any x coordinate and say, I want a graph that's a power series, but think about it as a sequence of polynomial approximators that's drawing closer and closer to this graph at that point, in the sense that it's matching its value, and it's matching its first derivative there, and then it's matching its second and third and so on derivatives there. So the Taylor series, not centered at 0, but the Taylor series just generally is going to be centered at some arbitrary point. People normally write A for that, centered at A. Okay? So it's going to involve the ith derivative of the series of the function evaluated at A, and it's going to have the I factorial piece, and the other bit is just a shift of what our powers are. And instead of x to the various powers, we'll shift things so that really A becomes the origin. We'll do a horizontal shift by A units, and we'll have x minus A to the I. If you add terms that look like that up from I equals 0 to infinity, you get an expansion that looks just like the function, but if you note the graph here sort of started its matching right at the origin. Well, this would be starting its matchup at some point x equals A. But you see how that's more general, I hope. So that's an intro to power series, and give you particular examples of Maclaurin and Taylor series. There's some just beautiful stuff we can now do now that we've got Taylor series. So I'm excited to talk about that on Thursday. Until then.